Welcome back to my rubber heart. Today we are diving into the world of resins, specifically the resins used in rubber compounding. Now, if you've been working in rubber long enough, you've probably heard of resins being used for tack, for reinforcement, for processing, even for surface finish or bonding. But what are these resins really doing inside the compound? How are they made? What kinds are out there? And how do you choose the right one? That is exactly what we are going to unpack in this episode. Let's start with the big picture. In rubber compounding, resin is a broad term that usually refers to low to medium molecular weight polymers or oligomers, typically thermoplastic or thermosetting in nature, added in small to moderate amounts to modify specific properties of the rubber. Unlike fillers or oils, resins don't just dilute or soften the rubber. They interact more selectively, often targeting the surface properties, the dynamic mechanical behavior, or the interfacial characteristics of the rubber matrix. And the way a resin performs, it's tightly connected to its chemistry, where it comes from, how it's made, and how it aligns with the polarity and structure of the base polymer. There are a few major families of resins we commonly see in rubber. One group is the hydrocarbon resins. These are synthetic resins produced through the polymerization of petroleum-based feedstocks like C5 and C9 olefins. You'll often hear terms like aliphatic C5 resin, aromatic C9 resin, or mixed C5-C9 resins. These materials are typically made using Friedel-Crafts catalysis or cationic polymerization, depending on the feed and target properties. What makes this resin so useful is their tunability. You can produce hard, brittle resins with high softening points that contribute to stiffness and tack. Or you can produce softer, more viscous resins that act as flow improvers or compatibility enhancers. Hydrocarbon resins are especially compatible with non-polar rubbers like natural rubber, SBR, and polybutadiene. They are widely used in tire compounding to enhance tack, reduce heat buildup, or fine-tune grip. Then you've got the rosin esters, which are bio-based and derived from pine trees. These come from natural rosin, which is a collection of mostly abiotic acid-type molecules, and are esterified using polyols like glycerol or pentaerythritol. Rosin resins are polar in nature and tend to be more compatible with polar rubbers like nitrile, chloroprene, or epichlorhydrin rubber. They are known for their exceptional tackifying power and are widely used in pressure-sensitive adhesives, sealants, and coatings. They also offer good oxidation resistance and a unique balance between flexibility and glassy behavior, depending on the molecular weight. There is also a family of phenolic resins, which serve an entirely different role. These are thermosetting resins created by the condensation of phenol with formaldehyde. Depending on the catalyst, acid or base, you get either Novolac or Resol resins. In rubber, Novolac type resins are often used as reinforcing agents, especially when cured with hexamethylene tetramine. These resins can cross-link with the rubber during vulcanization, forming a highly rigid, heat-resistant network. Phenolic resins are often used in brake pads, high-heat seals, and heavily loaded mechanical rubber goods. They bond strongly with certain fillers and fibers, and in blends with polar rubbers, they can even serve as curing agents themselves. Another fascinating class of resins include coumarone-indene resins, which are built from industrial byproducts of coal tar processing. These have good thermal and chemical stability, moderate tackifying ability, and can help balance hysteresis in SBR and NR compounds. They've fallen a bit out of favor compared to newer hydrocarbon resins, but they are still used in many high-performance industrial rubber compounds, especially where cost and heat resistance are key factors. Now, let's talk about how resins function inside the rubber matrix. Chemically speaking, resins don't usually participate in cross-linking, unless they are part of a reactive system like a phenolic resin. Instead, they physically interact with the polymer chains through solubility and compatibility. A resin that is well matched in polarity and molecular structure to the base polymer will dissolve or plasticize into the amorphous regions of the rubber. This can increase chain mobility, improve wetting behavior, and enhance interfacial adhesion. For example, when you add a hydrocarbon resin to an NR-based compound, it migrates toward the interfaces, helping to reduce surface tension and increase the contact area between rubber sheets, improving green tack. In dynamic applications, resins can also affect energy dissipation. They can increase the loss modulus in a specific frequency or temperature range, enhancing grip or damping, depending on the use case. In tire thread compounds, this is critical. You want the rubber to be slightly sticky and dissipative at the point of road contact, but still resilient enough to bounce back after deformation. By tuning the resin type, you can shift the tangent delta peak, the peak of energy loss, closer to your operating temperature, improving wet traction or rolling resistance as needed. Resins also shape processing behavior. A low softening point resin can reduce viscosity and improve flow, helping extrusion or molding. A high softening point resin might increase stiffness and dimensional stability, helping with calendaring or profile retention. Some resins, especially in combination with oils and plasticizers, act as co-solvents that enable better dispersion of pigments, fillers, or curatives. Others serve as internal release agents, preventing sticking in molds or mills. What's critical in selecting a resin is understanding which rubber you are working with. Non-polar rubbers like NR, BR, or SBR prefer non-polar resins, hydrocarbon or coumarone-indene types. Polar rubbers like NBR, CR, or ECO will perform better with rosin esters or phenolic derivatives. And the interaction doesn't stop there. You also need to consider other formulation ingredients. Oils can dilute the effect of a resin or enhance it, depending on polarity. Fillers can immobilize resin-rich domains or absorb the resin altogether if surface treated. And cure systems can limit resin migration, locking it into the matrix more tightly after vulcanization. In summary, resins in rubber compounding are much more than tackifiers. They are performance modifiers that operate on the molecular, interfacial, and processing level. They fine-tune how rubber flows, sticks, bounces, and holds together. Whether you are building a high-speed tire, a self-healing sealant, or a thermal-resistant hose, the right resin can make or break your compound. It's not just about adding something sticky. It's about chemistry, compatibility, and control. Thanks for tuning into my rubber heart. If this episode gave you a new appreciation for resins and their role in rubber science, give it a like and subscribe for more. And if you are struggling with a compound that won't tack, won't flow, or just won't behave, drop your question in the comments. I would love to help. See you next time.